Hi everyone, I'm Elena Selmi. I'm an undergraduate student at the University of Oxford. And in case you've not heard enough of them yet already, I'll be talking about lunar solar simulants, but from the perspective of optical properties. A quick summary of my talk. I will be talking very briefly about lunar regolith simulants that we used, which Brandon also just talked about because they were the Exolith LHS1 and LMS1. I will explain and introduce the instrument that we use at Oxford to measure optical properties and why it is advantageous to use it. And then I will present the BRDS. There's a lot of acronyms in this talk, so I'm sorry about the long title, but it's actually acronyms. The BRDFs for the soil simulants that we looked at. So we were contacted by a company that asked us to measure scattering properties for these two new simulants from the Exolith lab that throughout the week were at the front of the room, and luckily they're not there anymore, to assess similarity to return Apollo samples for future rover ground testing. Why optical properties are important and are interesting for lunar solar simulants, because they can be used to compare to visible remote sensing measurements from the lunar surface. They can be compared to previous literature and to photometric models like the HAPKI model. These are the simulants that we looked at. As Brandon just said, they were designed to have a mineralogy very similar to returned Apollo samples, and were designed to mimic and simulate accurately the mechanical properties of Apollo return samples. But as of now, we're not aware of any investigation of the optical properties for these simulants. The visible Oxford Space Environment goniometer is a goniometer, which is an instrument that allows for measurements of the reflectance of opaque surfaces from a range of different angles. The way it works is that we illuminate using a halogen lamp that is off screen. We use a fiber optic to illuminate the sample at various incidence angles from 0 being nadir, to 60 degrees. And then we have a detector that measures the reflectance at different angles from 0 to about 70. And we can also rotate the main axis to have azimuthal range. We're in the wavelength. Bozek used to be vacuum instrument, but it was modified over the years to be in the wavelength. And this is the range that we can look at now. Why is it interesting? Why is it important to have a 3-axis range freedom? Well, there's a number of reasons. Most of your standard mass spectrometer in the lab measures only from nadir, but it is interesting to be able to measure things from an off-nadir angle, because it's something that we do on the moon. It's done by LROC, it's done by Diviner, it will be done by future missions. And so being able to do it here on Earth allows for calibrations of these instruments for future and past missions. And we've heard a lot about PSRs. Bryce Mahanti had a beautiful animation yesterday that explained very well what they are. By definition, they are areas on the moons that are not directly illuminated by the sun. And so anything that goes into it is actually reflected, as you can see in the picture, is reflected off other surfaces on the moon. So it's important for us to be able to know how the moon scatters light into the PSRs, because this allows for all thermal modeling and modeling of the heat flows, which is the subject of so many of future missions. And current missions, LROC does it, MQ Bonchan 101 does it, and Lunar Trailblazer will do that as well. Also, our VOSEC has already looked at previously returned Apollo samples. So it allows for a very direct comparison, and this is what I'll show in a few slides. But this is what was done a few years ago when the Apollo 16 and Apollo 13 return samples were looked at by another PhD student in the group, and were compared to the Bloomsburg University goniometer, which is a goniometer that is not operating anymore. I'm only going to point out here that as we saw in the technical list, Bose doesn't do less than 4-degree phase angle. Well, bug used to do it, but you can see in the plot, the colors are not really good, but basically green is bug and orange and blue is Bose on Apollo 11, Apollo 16. You can see the opposition effect that is starting to show, the opposition effect being the superlinear behavior that regolith exhibits when the light, the sun is directly incident behind the detector. And I'll mention that later as well. But you can see that bug showed very well the opposition effect, and Vosek followed in a bigger step range the same behavior. So bidirectional reflectance distribution functions, what are they? Well, it's just a function of 4 variables that takes the reflectance incident, like the incidence and reflectance, directions and returns, the ratio of reflected radiance to incident radiance. This is another example of the angles and how we define them from the nadir, which is the same that I reproduced on the Bosek picture. So before looking at the lunar soul simulants, we obviously had to recalibrate the instrument to make sure that we could compare directly to the old and to the previously made Apollo measurements. And so we use the widely diffused commercial wide spectralon, and you can see that the calibration is very similar to what was previously done in Curtis et al. So we are confident that our calibration is correct and the measurements can be compared quite directly to the Apollo. So these are LHS1 and LMS1 in the principal plane being 0 to 180 degree azimuthal. And well, this is interesting just because it shows that we can kind of see for all the different incidence angle that we do have somewhat of an opposition effect starting to show. We've heard a lot about Neil Armstrong, and I swear this is the last mention that I think we're going to hear this week. But if you remember the infamous picture that he took on the moon when the sun was directly behind him and his shadow had that halo, that's an example of the opposition effect. Back then he was in a mare, and the mare is more backscattering, and this is also what we're going to see the simulants do. It's more interesting to see what how the simulants do compared to the Apollo samples. The simulants here are red for LMS1 and blue for LHS1, and yellow and black. You can kind of see them. Yellow and black are Apollo 16 and Apollo 11 respectively. And you can kind of see that the blue does quite well compared to Apollo 11 and Apollo 16. The red, which is the Highlands, not as much, but this is expected because actually Apollo 11 and Apollo 16, well, Apollo 11 is a Mare Tranquillitatis sample, so it's fully Mare. And Apollo 16 is at the edge of Mare and Highland. So we would expect the Mare to do better than the Highland in this respect. So this is in the 90 azimuthal angle, and you can see kind of the same trend. So it is more interesting to look at LMS1 in comparison to Apollo samples. And what we can see is that it does quite well. We've done 60, 15, and there should be in the middle 30 degrees incidence angle. The 30 degrees basically is in the middle also for what concerns average similarity and maximum discrepancy. So in the 15 incidence angle range, the LMS1 does really well with an average similarity of 3.2% and a maximum discrepancy of 13.7, with that happening actually where the opposition effect takes place. And as I said before, Bosek has some difficulty in measuring very close to 0 phase angle. So this is good. If we take this out, the similarity is very close. The similarity decreases at 60 degrees incidence angle, but we're still at the very maximum, less than 30% away. So overall, LMS1 does quite well. Looking at LMS1 and LHS1, we can point out some of the features of the Highland. which is, we can see that the red, which is LHS1, as we expected, scatters quite uniformly backward and forwards, while the mare is a lot more backscattering, which again is something that we sort of expect because as we saw in the geotechnical properties screen, which I just took off their website, the Exolith Labs website, the highland is mainly an orthosite, and an orthosite is more forward scatter, like it's, well, it scatters very well forward, but we expect the basaltic mare to be more backscattering. And it is just the weird outlier is the 15-degree incidence angle, which is the one that the mare does the best compared to the Apollo samples. And here, the highland and the mare both scatters quite uniformly forward and backwards. But again, since this is the best similarity to the Apollo samples, we still consider this positive. To conclude and summarize, we've measured the BRDFs of Exolith Labs LHS1 and LMS1 with a range from 15 to 16 incidence angles and -70s to 70 reflectance angle. We found that the average similarity of LMS1 to Apollo 11 return samples is 3, 5, and 8% for the 15, 30, and 60 incidence angles. And the maximum discrepancy is below 30%. And the LHS1 sample is less backscattering than LMS1, which is what we would expect for highlands with respect to mare simulants. For future work, we would like to look at actual measurements of nadir or of instruments on the moon, because that would allow us, for example, from LROC or Diviner, because that will allow us to have a more direct comparison to LHS1, the way we've done for LMS1 and the return Apollo samples. Thank you for listening. I want to thank you, the ELS Travel Grant, for giving this presentation possible, and obviously Neil, Catherine, and Tris for giving me this opportunity to be here. Thank you.